We're going to talk about Gauss's divergence theorem, part one. We have a solid region here. Omega is the solid region, and then S is the surface bounding the solid region. It's got to be a closed surface. Can't leave any pieces off. And then the divergence theorem says we can integrate over the surface f dot n dA. We'll talk about this in a minute. And we get the same thing as if we do a solid integration. This would ordinarily be a triple integral of div f dv, where dv is an element of volume, could be dz dy dx, dz r dr d theta, or rho squared sine phi d rho d theta d phi in spherical coordinates, depending. First of all, a little bit of explanation. This n hat is a unit normal vector. It's going to be perpendicular to the surface and of length 1. And so over here, the unit normal vector is j. Up on top of this cube, normal vector is k, points upward. Down here, negative k. Along the x-axis, pointing out from the face, it's going to be I. And back this way, it would be negative j. There's going to be a negative I back here. I didn't write it, so I didn't want to cloud the picture. That's what this means. Now, a little bit about this before we get into evaluating both sides to show what this really means. We want to talk about this quantity here. This quantity right here is flux. And if that side is flux, this side must be flux. Well, if this is volume, this must be, div f must be flux per unit volume. It gives us a physical interpretation of the divergence. It's sometimes called the flux density. Flux per unit volume times volume gives you flux. And let's, dimensionally speaking, look at what this actually represents before we dig into the theorem. Suppose we have a horizontal plane here, 2 meters by 2 meters. It's horizontal. Our normal vector is k, and suppose we have this f vector sticking off a 45-degree angle. It's going to be 2j plus 2k. We go over and up in equal measures. That's why I know that's 45 degrees. And let's suppose that's meter per second. That would give us a velocity field. Yeah, this is going to be the same. This f is going to be the same anywhere on the surface. It's a constant vector field. This could be something moving through the surface. Could be air moving through this air duct, for instance, and it's moving in this direction. This speed turns out 2 square root of 8. It'd be roughly 2.2 meters per second. It's moving through this surface. Now, dA is 2 times 2 square meters, 4 square meters. That's area of the square. F dot n is 2j plus 2k dot k. Okay, it's 2 times 0 plus 2 times 1. 0 plus 2, which is 2. And when you dot it on a vector, we retain these units, meters per second. Now, if you do f dot n dA, that's 2 meters per second times dA is square meters, and it gives you 8 cubic meters per second. That's volume per unit time, and that's a unit of flux. Okay, that's that 4-letter F word you often hear in a physics lab in Physics 2. Flux. And very easy to visualize that this is a velocity field. In electricity and magnetism, you do all these flux relationships, and if you keep velocity in mind, it's easier to remember keep your feet on the ground and your bearings. Now, what we're going to do in a minute, we'll do this in a second video. We'll actually start with this solid, the Cartesian product 0 to 2, 0 to 2, 0 to 2, which we can represent with this cube. And I'll give you a vector field. We're going to evaluate this side and this side. This side will be easiest, and then this side, what we'll do is we'll pick it apart side by side, 6 different surfaces, and we'll evaluate each surface added up and show that that adds up to this. So that's the end of part 1.